Hi, Assalamualaikum warahmatullahi wabarakatuh, and a very good day to everyone. We're going to continue our lesson today on the EAN rule, the 18 electron rule, or effective atomic number rule. Before we proceed, I would like to thank you for your uh, active participation in our discussion last week. So for this week, inshallah, we are going to have 2 or 3 more videos to cover our syllabus. So bear with us, and inshallah by 28 April, the MCO will be lifted, but these online classes will be going on as usual. Now class, we had covered this particular syllabus before we left uh, before PKP. So the 18 electron rule, the EAN rule, is not something alien to you. I hope so. But there's no harm in refreshing this syllabus. So as I said in the class, if you still remember that before this you learned that for an atom to be stable, it must have 8 electrons in the outermost shell. And today we are going to learn that in order for the metal to be stable, it must have 18 electrons in the outermost shell. So why so? Because remember, for every orbital, the number of electrons maximum that can be occupied is 2 electrons. So knowing this, we can assume that to accommodate 18 electrons, you must have 9 orbitals. So why you have 9 valence orbitals to be filled for transition metals? So in the case of first transition series, you can see in your periodic table of your transition metals, these orbitals are actually consisting of 3D, 4s, and 4p. So for 3D you have 5 orbitals. For 4s you have 1 orbital, and for 4p you have 3 orbitals. So when you sum all these orbitals together, the number of orbitals that you're going to get is 9 orbitals. So that's why you have 18 electron rules. Okay, remember, effective atomic number, or EAN, is actually counted for the number of electrons in the given metal atom, meaning even though your metal is forming a complex with your ligand, but we are going to calculate the total number of electrons in the complexes, but we are going to calculate the number of electrons in your atom. So EAN representing the number of electrons per given atom. Okay, so what are the electrons anyway? So for the normal atom, isolated metal atoms, non-bonding metal atoms, the normal configuration would be Ar, argon, as you can see here, for S2, 3d10. But when you complex a metal with ligand, the energy of your d orbitals will be dropped. So that's why it is safe for us to say that the valence electrons are going to be filled in d orbitals of your metals. And of course, there are certain cases where we can see for S2, 3dx exist, but as far as your syllabus is concerned, we are going to assume that only d orbitals are going to be filled up with your electrons. So therefore, when you want to count the number of electrons for your metal, it's very easy, because for zero oxidation state metals, or zero valent metals, non-bonding metals, the number of electrons should be in corresponding to the column it occupies. Meaning, for example, iron is in the 8th column, so we call it D8 metal. So if it is located in the in the 7th column, we call it D7. Like, look at this rhenium, it is Re3 plus. So, or we call it D4. So actually, rhenium is coming from 7th column, so it should be D7, but you have to minus 3 electrons in order to become 3 positive. Remember, the more electrons you donate, the more positive your atom will become. So we now understood how to assign the number of electrons to your metal center. Now these are the rules that you have to obey when you count the EAN. First one is easy. For carbonyl, for example, for carbonyl ligand, it is always 0 charge because it is a neutral ligand. But the number of electrons that carbonyl can donate to your metal is 2 electrons. So different ligand will have different number of electrons. Sometimes they have the same number of electrons, sometimes they can have different number of electrons. It depends. So how do you know? You have to see table 1 on page 11. Let us scroll down a bit on page 11. Yeah, 5 more pages to go. You will see this table. So ligand and number of valence electrons contributed. So you see that your carbonyl CO is here. So that's why carbonyl can donate 2 electrons to your metals. Now going back to your rules just now, how to count effective atomic number. So number 2, for polynuclear complexes, meaning you have more than one metal in the complex, we are counting electrons for the compound as a whole. So each M to M, metal to metal bond, carries 2 electrons. But since EAN is actually total number of electrons in the given metal, meaning individual metal, so you must find the number of electrons in that one metal. So instead of counting 2 electrons per bond, it's going to be 1 electron per metal. I hope you do understand this. Okay, if you don't, do not hesitate to ask me later in the WhatsApp group or in our Padlet platform. Number 3, find the electrons belongs to the metal. I've explained this slightly earlier. It depends on location of your metal in the periodic table. But if it is positively charged, you have to minus the number of electrons accordingly. But if it is negatively charged, you have to plus the electrons accordingly. Last but not least, you have to sum all the electrons up, and the number of electrons must be 18 electrons. Only then it is considered stable. If it is less than 18, it is not stable. Now, let us look at an example. So the first one, can you name this compound? Count electrons in MoCO6. So Mo is molybdenum. We have CO carbonyl, so we can call it hexacarbonyl molybdenum or molybdenum hexacarbonyl. So let us look at the structure, the chemical structure of this complex on page 8. Let us observe. This is your mononuclear M, can be any metals, but in this case molybdenum with 6 carbonyl. So you see, we have 6 carbonyl and 1 metal here. Now let's go back to this example. So this is neutral binary carbonyl. So the metal oxidation number is always 0. So how do you know whether your metal is charged or uncharged? It depends on the ligand. If your ligand is neutral, your metal is going to be 0 valent. If it is not neutral, meaning your ligand is negatively charged or positively charged, so the charge or oxidation state of your metal will be changed accordingly. So now molybdenum is coming from 6 column in the periodic table, so that's why the electrons 6. So your carbonyl, we have 6 carbonyl. 1 carbonyl carries 2 electrons. So 6 times 2, 12 electrons. When you total up, you are going to get 18 electrons. So molybdenum hexacarbonyl is considered stable. Okay. Now for number 2, count electrons around each uranium in Re2CO10. So for this one, I need you to give me the full name of this compound. Before we go further, let us see the structure. Figure 2, page 8. Figure 2, page 8. Okay, this is figure 2. So M can be any metal, but in this case, it is rhenium. So 1, 2, 3, 4, 5. So 5 carbonyls attached to one metal. So 1, 2, 3, 4, 5. So 5 ligands also attached to one metal. So meaning to say, every metal has 5 ligands attached to it. So let us see how do we calculate or count the effective atomic number. So first, for the metal, easy, is 7 electrons because coming from 7 column, and we have 5 CO. We don't count 10 CO because it is symmetrical. So 5 CO, 1 CO carries 2 electrons. So times 5, you're going to get 10 electrons. And then we have metal to metal bond. Remember I told you just now that we're going to calculate only for one metal. So for one bond is 2 electrons. So 2 times half, you're going to get 1 electron. So there is no 2 here. Okay. So the total electrons for this compound is 18 electrons. So it is also stable. So for example number 1 and 2, I think it is quite easy for you to understand. But let us see example number 3. So for this particular complex, I want you to find the name for this complex. Okay. So let us see the figure 3, page 8. Figure 3, page 8. The structure is gonna be a little bit complicated. Okay, this is figure 3. You see, now you have how many metals? 3. 3 iron here. So how many carbonyls in total? So you see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So in total you have 12 carbonyls and also 3 iron. But those are not the only things that we have to look at. So there is extra information that we need to extract from. So the first one is actually this carbonyl bridging to iron. This carbonyl also bridging to iron. So in this case, we understood that we have 2 bridging carbonyls or bridging ligands, because these 2 carbonyls bridging to iron metals. Okay, and this one is unbridged, meaning there is no bridging carbonyls that bridge this iron to another iron. So we call this iron as unique iron. Now how do we calculate this? Okay, so we have 10 terminal carbonyls and then 2 bridging carbonyls. And how do we calculate this? Let us see. Now we have iron. Iron is coming from from 8 columns, so it's going to be 8 electrons. 0 charge because you have all neutral ligands, so there's no problem here. We have 3 CO with 6 electrons. So why 3 CO? Now remember, we are actually calculating the EAN for this bridging iron. So why it is 3? Now let us look at this figure again. Okay. So for this iron, this bridging iron, we have 1 bridging ligand, but we have 3 terminal ligands. So that's why we put it as 3 times 2. Okay. So 3 carbonyl ligands. So it is 6 electrons. Now we look at this. This is bridging ligands. How many bridging ligands do we have? We have 2 bridging ligands. So one bond of carbonyl can give 2 electrons, right? So we need to multiply by half to find one carbonyl ligand. Okay, so you're going to get 1 electron. But since we have 2 bridging ligands, you have to multiply by 2. So let me rephrase this. Okay, it might sound a little bit confusing. So we have 2 bridging ligands here, but for one iron metal, okay, you have 1 bridging ligand. Let me see here. We have 1 bridging ligand attaching 2 metals, another 1 bridging ligand attaching 2 different metals. So now we are calculating this, it's going to be 2 electrons, right? But since these 2 electrons, for one metal, it should be 1 electron. Now for another carbonyl ligand, it's going to be another 1 electron. So total is 2 electrons. Okay? If you don't understand this, please ask me. Okay? I understand that this sometimes can be a little bit confusing. Okay? So 2 electrons total, and we have last one, iron to iron. So iron to iron, we have 2 electrons. Any metal to metal bond must be comprising of 2 electrons. And then, but for one iron, it's going to be 1 electron. Right? But you have to multiply by 2. Why? Okay, in this case, each iron has 2 metal to metal bonds. So this one iron has bond with this metal. This iron also has bond with this metal. So one iron has 2 bonds. Okay, so that's why you have to multiply by 2. So when you total up, you're going to get 18 electrons. So this is stable configuration. But wait, we're not done yet. We have to calculate the unique Fe. Unique Fe meaning one without the bridging ligand. So how do we calculate iron? 8 electrons, easy. So we have 4 carbonyl. So 8 electrons. Okay, let us double check. So for this iron, you have 1, 2, 3, 4 carbonyls. So 4 times 2, you're going to get 8 electrons. So for iron, okay, so for this iron, it has 2 metal to metal bonds. So 1 bond, 2 electrons, but for one atom, it's going to be 1 electrons. But since we have 2 metal to metal bond, it's going to be 2 electrons. Okay, so the total is going to be 18 electrons. So this complex is also considered stable. Now, what if you're not given with any chemical structure? Can you count the EAN? The answer is yes. So without the chemical structure, we will never know whether we have bridging ligands or not. So we have just calculate the normal way, meaning we can not consider the presence of bridging ligands. So we have 3Fe, am I right? From the chemical formula, we do understand that it's going to be 3Fe. Let me check. 3Fe and 12CO. Okay, 3Fe, so 3 times 8 is going to be, 3 times 8 is going to be 24. And then 10CO, or in this case, since we do not know that your bridging ligand is present, so 12, 10 plus 2, 12 times 2 is going to be 24. So 24, 24, 48. Now we have 3 iron to iron bond. So 3 times 2, you're going to get 6. So 24 plus 24 plus 6, you're going to get 54 electrons. But these 54 electrons is actually the number of electrons for the whole complex. We want to find EAN, meaning what will be the total number of electrons for one metal atom. So since we have 3 metal atoms here, 3 Fe, you have to divide 54 by 3. So the answer will be 18 electrons. So it is still considered stable. So from this lesson, from this particular example, for the third example, what I would like to emphasize is that we can calculate or count the EAN, one, if the chemical structure is given, and second, when the structure is not given. We can totally depend on the chemical formula. Okay, if you don't understand it, please ask me questions. Do not keep it to yourself. Okay, and last but not least, count the valence electrons for this compound. This is another compound that you have to give name to. Please give me the name of this particular complex. So look at this. We have carbonyl and we have also chloride. So chloride in this case is negatively charged. It is not a neutral ligand. So from this information, we understood that your molybdenum also is not going to be neutral. It's not zero valent metal. So for MO, it's going to be positive 1 to balance negative charge from chloride. So MO is coming from group 6, from column 6. But since it has positive 1 charge, we have to minus 1 electron. Chloride, negative 1, obviously. How do you know it is 2 electrons? You have to refer to the table as I have shown you earlier. And it is 5 carbonyl. So 5 carbonyl times 2 is going to be 10 electrons. When you total up, it's going to give you 17 electrons. So this obeys 18 electrons rule. So this particular complex is considered unstable. Okay, so I think that's all for now. I'm going to be giving you more videos later. So you have few questions that you have to answer here on the naming of the complexes, as well as I want you to do this practice exercise, write all the answers on the paper, and then you take the picture of the answers and please upload under this video on the Padlet. Okay, see you in the next video. Thank you very much.